These are some review problems for a first exam in a Calculus 2 class. First question we're going to look at says to evaluate the following definite integral. And we've got an integral from -2 to 1 of 3x plus 1 to the 4th dx. Okay, so this one, fairly typical. It's going to be a substitution problem. So what I'm going to notice is that this 3x plus 1 to the 4th, I mean, you could expand that out here, but it's going to be simpler, to just let u be 3x plus 1. And then du is going to be 3 dx. We make a substitution here. So when we substitute those in, 3x plus 1 becomes u to the 4th. Dx, well, we have du equals 3 dx. So we'd like to have a 3 in the dx. Well, we can compensate for a lack of a 3 by a 1/3 here, and we'll get a du. Another way to look at that is that dx, if we divide by 3 and du equals 3dx, dx would be 1/3 du, and then sort of have a 1/3 du, but I wrote the 1/3 out in front. Now the bounds, I'm going to tend to convert to u bounds. So this -2, that's an x equals -2. So 3 times -2 is -6, plus 1 is -5. So x equals -2 corresponds to u equals -5. And then x equals 1 is 3 times 1 is 3, plus 1 is 4. So in u range, we're going from -5 to 4. Okay, now we're going to evaluate this, or do our antiderivative, I guess. So we get 1/3. Antiderivative of u to the 4th is u to the 5th over 5. And we're going to evaluate from a u goes from -5 to u equals 4. So 3 times 5 gives us 1/15 of 4 to the 5th minus -5 to the 5th. So if you look this up, or you work this out, you get 1/15, 4 to the 5th. The minus 5 to the 5th will become like -5 to the 5th, and then the negative will sort of cancel out the negative, so we get 4 to the 5th plus 5 to the 5th. Now, this is the kind of thing that I would go use a calculator for. So I'm going to do a 4 to the 5th plus 5 to the 5th. Just see what we get. 4149. Whoops. Over 15. And I might wonder if, can I simplify this? Is there a factor of 5 on top? No, it doesn't end in a 0 or 5. Is there a factor of 3 on top? Well, maybe here. If I add up the digits, 4 plus 1 is 5, plus 4 is 9, plus 9 is 18. That means there is a factor of 3. So let's just do our divide by 3. We get 1383. So this is 1383 times 3 over 3 times 5. The 3's cancel, and our answer ends up to be 1383 over 5. Okay, next question. I'm going to evaluate the following indefinite integral. So this one, we've got x minus 4 over square root x squared minus 8x plus 1 dx. Now, this looks a little bit tricky, but we're going to do a u substitution again. And one thing to try here is to let u be the thing underneath the square root. And then you kind of hope that things just simplify here. So I'm going to let u be x squared minus 8x plus 1. And then du would be 2x minus 8 dx. Now, okay, so I then make the bottom square root of u, but I have this x minus 4 on top. I have 2x minus 8 here. Those are different, but if you notice, this is actually, if you factor out the 2 times x minus 4 dx. So that x minus 4 I have on top lets me know that probably the substitution is going to work out. So I've got the x minus 4, I've got the dx. I don't have the 2. So I'm going to sort of compensate for that. Write this as 2 times x minus 4 over square root x squared minus 8x plus 1 dx. But that multiplied by 2 I added, I have to divide by 2 on the outside, or multiply by 1/2. Now I can substitute in the u's. So I get 1/2 integral 2 times x minus 4 times dx gives me a du. And then I have 1 over square root of x squared minus 8x plus 1. That's 1 over square root u. And now I'm just going to evaluate this. Let me just rewrite it. 1 over square root of u is u to the -1/2. And then when I do my integral, I get 1/2 times u to the add 1 to -1/2 gives you a 1/2 divided by 1/2. Note the multiply by 1/2, divide by 1/2 will cancel. You get a plus c. So we've got an answer in terms of u now, but we need an answer in terms of x because the original antiderivative was in terms of x. So we're just going to substitute in for u, we're going to substitute back the x's. So what I end up with finally is x squared minus 8x plus 1 to the 1/2 plus c. You might write that to the 1/2 as just square root x squared minus 8x plus 1 plus c. You really don't need to do this as a square root instead of to the 1/2, but either that sometimes makes it look nicer. Next problem. Okay, we're supposed to estimate the value of the following definite integral using 3 rectangles and right endpoints. So we're going to do an integral from -2 to 1 of 3x plus 1 to the 4th dx. So if you think back here, we did problem 1 up here. We evaluated this same integral. We got an actual value of 1383 over 5. So let's actually compute. We got the 1383 divided by 5. Let's get a number there. So it's like 276. So we suspect, when we do 3, we should get something close to 276. So let's just draw sort of what's going on here. So what we're going to get is we're going to get our rectangles. Let's see, we've got some function, from -2. -1, 0, 1. Now we could graph this to get a sense of what's going on here. Don't really need to do this. 3x plus 1 to the 4th. Let's graph, and I get kind of a mess. So I'm going to change my window. How about -2 to 1 for the x? And I'll graph. Let's see if that looks a little nicer. You get somewhat of a sense of what's going on. We're getting much bigger numbers here. So again, well, let's just go to zoom. Now let's do the window. Y min, let's see, at -2, we're going to get like -6, about 5 to the 4th. It's like 625. So we're going to do, well, they're all going to be positive because it's to the 4th, so let's go -1. How about like 630? Let's graph that. And there you get a sense of what's going on. So this looks more or less like a parabola here. That's a degree 4, so it's not really a parabola, but my graph is going to do something, let's see, at some point at, I guess, -1/3, it's going to hit 0. And it's going to go up here somehow. So we're going to get this kind of graph, and we're trying to find the area underneath this curve. So really this shaded region here. Now to do that, we're going to use 3 rectangles and right endpoints. So the first rectangle is going to go from -2 to -1, and the right endpoint means the height of that rectangle is going to be the function value at -1. Second rectangle is going to go from, so we do a green, -1 to 0, and our height is going to be the function value at 0. Note that's not, it's 1, it's not actually 0. And third rectangle, let's go back to red. Here we're going to go from 0 to 1, and then our function value, or our height, is the function value at 1. So we're going to get this rectangle here. So we're going to approximate this area of the curve with the areas of these 3 rectangles. Now, what we're going to get then, if you think about that, is that this here is going to be what should be the width of a rectangle. That's 1, so it's not going to change anything. So we'll take the width times the height. Height here is f of -1. So that's 3 times -1 plus 1 to the 4th. So that's the first rectangle. Second rectangle, we have a 1 times 3 times the right endpoint is 0 plus 1 to the 4th. Third rectangle is 3 times, we're using a right endpoint of 1 plus 1 to the 4th. So when we evaluate those, let's see, 3 times -1 is -3, plus 1 is -2. So I'm going to end up with -2 to the 4th, times 1 doesn't do anything. This one, 3 times 0 is 0. I'm going to get a plus 1 to the 4th. Here I'm going to get 3 plus 1 plus 4 to the 4th. So what I get, -2 to the 4th is like 2 to the 4th, that's 16. 1 to the 4th is 1. 4 to the 4th is 2 to the 8th, which is 256. And if you add those up, 16 plus 256 is 272. Our answer here turns out to be 273. And you look back at the answer to number 1, the actual area was 276.6, so pretty close. Gives you some sense that likely both of these are correct, or at least close to correct. So in this problem, we're supposed to evaluate indefinite integral. We're doing an integral of 3x times e to the x squared dx here. Our general strategy is we're going to take this x squared here and let that be u. So this is going to be a substitution. I'm going to let u equal x squared, and then du will be 2x dx here. And the idea here is we have u as x squared, and then we have an x out in front, and that's going to help with that x there. So what I'm going to do is I'm going to rewrite this. I'm going to pull the 3 out in front, derivative. I'm going to write the e to the x squared first, and then times x dx. But I want to get a 2x dx, so I'm going to add a 2 there. But I can't just multiply by 2, so I'm going to multiply by 1/2 somewhere else. I'm going to choose to do that out in front. And now I'm going to do my substitution. 3 times 1/2 is 3/2. E to the x squared is e to the u, and then this 2x dx is du. Now I need to integrate, or do an antiderivative. Antiderivative of e to the u is just e to the u, get a plus c. And then I need to change my u's back to x's. So my answer should always be in terms of the original variable, which is x. So I get 3/2 e to the x squared plus c. And that's my answer. Next one. We're going to find the area of the region between the graphs of y equals 3x and y equals x squared plus 5x minus 15. So let's do a quick graph here. Let's just go to our graphing calculator. We'll get 3x, and then it was x squared. Let's move this over so we can see it. X squared plus 5x minus 15. I'm going to go to graph. I think I've got a funny window here. Scroll back over. That window's not really showing me much, so I'm going to go to zoom. How about zoom standard? Might go to zoom fit. There's our line. There's our parabola we can see. So let's go to zoom. Let's see if zoom fit helps. Here it does that. There's our line. Then we get a parabola that comes down like that. So we get a sense of the picture. So if our sketch here, probably could have done this without the calculator. Y equals 3x is some line with a positive slope, like this, goes through the origin. And then we have a parabola that opens up. So that parabola is going to go down here and hit there. So I don't really know what these intersection points are. I guess I can look at my graph. It's either there and there. It doesn't matter so much what the height is or what those intersection points specifically are in terms of doing the calculus. Now what I do need to do is find the x coordinates of those intersection points. To do that, I'm going to set 3x equal to x squared plus 5x minus 15. So at those intersection points, the y's are equal and the x's are equal. So I need to solve this. I'll move the 3x to the other side. I'll get 0 equals x squared plus 2x minus 15. If you factor that, let's see, we'll get x plus 5 times x minus 3. And so we'll get x equals negative 5 or x equals 3. So that means we get one intersection point is 3. We could use the 3x is 9. We plug in 3 here, it should give you the same thing. Other intersection point is negative 5, comma, negative 15. So those are our two intersection points. Now to find the area, I could do either vertical rectangles or horizontal rectangles. Vertical is going to be easier, and the reason horizontal is not probably a good choice here is that as I look at the bottom of the parabola, if I go left to right, sort of with a slice, the left half is the parabola, right half is sort of the other half of the parabola, so I'd have to take this x squared plus 5x minus 15, solve for x. That's going to involve completing the square probably. Might not be something you really want to do. And 1/2 will be a positive square root, 1/2 will be the negative square root, sort of part of that. But you'll notice on the left, this left function goes from that part of the parabola back to the line. That means I'm going to have two integrals if I do a horizontal split, do it sort of as a dy. So I'm going to choose not to do that. So we can erase that. Whoops. Let's undo erase. Undo our ink strokes. There we go. So we get rid of that. Okay. So instead, I'm going to do vertical rectangles. And the nice thing about this is the top function is always a line, bottom function is always this parabola, and they're both already solved for y, which is what I need. So my area here, I'm going to integrate my vertical rectangles. These are sort of based or indexed on x. So I go from negative 5 to 3. And it's just going to be the top minus the bottom. So the top function is 3x minus the bottom function is x squared plus 5x minus 15. And then I'm going to use a square bracket on the outside just to differentiate from the parentheses. And then the sort of dx or delta x would be the sort of width of one of these little tiny rectangles. And so we wrote down an integral here. Now we just need to evaluate this. So I'm going to get an integral from -5 to 3. I'm going to get 3x minus x squared minus 5x plus 15. The negative distributes. I can combine the 3x and the -5x. So I get an integral from -5 to 3. Negative x squared minus 2x plus 15. One thing to keep in mind here is I should be getting a positive answer because it's an area. It concerns me a little bit these negatives, but I have the positive, so maybe it'll work out okay. And then I'm going to do my antiderivatives. I'm going to get a negative x cubed over 3. Antiderivative of x is x squared over 2, so I'll get a negative x squared. And then I get a plus 15x. And I'm going from x is -5 to x is 3. So I get a negative 3 cubed over 3 minus 3 squared plus 15 times 3. And the 3 minus, plug in the -5. -5 cubed over 3 minus -5 squared plus 15 times -5. And what I'm going to get here, let's see, 3 cubed over 3 is going to be 3 squared, so that's a -9, minus 3 squared is 9, plus 45. Here I get negative to the third, that's going to be negative. Another negative makes it positive, but the other negative makes it negative. 5 to the third is 125 thirds. -5 squared is 25, so I get a minus 25. And then I get a negative 75, but the minus makes it a plus 75. And I think I made a mistake. -5 squared is -25, but then I have a minus here. So that negative subtraction with the 25 should be an addition. Okay, so now I get this. Let's see, if I do this by hand, I get 75 plus 25 is 100, plus 45 is 145, minus 18, minus 125 over 3. 145 minus 18 is 127. Minus 125 over 3, let's see, 363.81 over 3, minus 125 over 3. If I did this correctly, I should get 266 over 3. 6 plus 6 is 12, plus 2 is 14, not a multiple of 3. Now, I did all this arithmetic by hand. On an exam, what I'd probably do is get here and then go appeal to the calculator. So I would get there and say, I don't know if I trust my arithmetic. To be honest, I'm not sure I trust mine right now. So we'll see what happens. We get a new parentheses, -3 to the third divided by 3 minus 3 squared plus 15 times 3 minus, we have a -5 to the third divided by 3 minus, I guess it's -5 squared. Sometimes I just do the 5 squared, seeing the negative would cancel. Plus 15 times -5. Close parenthesis, close other parenthesis, hit enter. I get that, and then I could go math to a fraction. Spits out the 256 thirds. I think I just messed up my subtraction. 381 minus 125. Yeah, so I just messed up my subtraction, which is the exact reason I'm using the calculator, because I worry that I'm going to just mess up the arithmetic. So this shouldn't have been 266. Switch it back to blue. 256. And again, 6 plus 5 is 11, plus 2 is 13. Divided by 3 will not simplify. Next question. So we're going to find the volume of the solid formed by revolving the region bounded by y equals x minus 2 squared and y equals x about the y-axis. So first thing I'm going to do is try and draw my region. X minus 2 squared is a parabola. So I'm going to go down, hit at 2, and go back up. So that should be at 2. And y equals x is going to go like this. So the region oh, it's going to go like this. And then I said the region bounded. I'm like looking down here, but that's not right because it doesn't say I'm bounded by the x-axis. This region is going to go back up and clip this drawing. So I'm really looking at this region here. I'm going to redraw that because my scale is not good. Let me just redraw this to the right here. So I get my parabola like this, and then my line is going to go up like this here. So the parabola should hit there, but I'm going to get an intersection point there and there. So this is the region, and we're trying to revolve or rotate about the y-axis here. So again, I don't really care specifically what the region looks like. I just want kind of a schematic drawing. Now, what I'm going to do first of all, let's find the intersection points. So I have x minus 2 squared equals x. I'm going to solve that. I think I'm going to have to expand x squared minus 4x plus 4 equals x. Move the x to the other side. I get x squared minus 5x plus 4 equals 0. And then I can factor. I get x minus 4 times x minus 1 equals 0. That gives me x equals 1 and x equals 4. So our intersection points, this one is 1, 1. This one should be 4, 4. You can check. I'm using the y equals x equation because that's easier. You can check with the other equation. 1 minus 2 is negative 1 squared is 1. 4 minus 2 is 2 squared is 4. So those are definitely 2 points on both equations, or the graphs of both equations. Okay, now we want to choose, do I want to use really vertical rectangles or horizontal rectangles? So when I look at this, what I'm going to think is that if I use a horizontal rectangle, I'm going to run into a problem on the bottom. I think we did this in a previous question, where I have on the left, with horizontal, I'm going to get the part of the parabola on the left down here for y goes 0 to 1, and then y goes 1 to 4, I'm going to get the line. That means I'm going to need at least 2 integrals to do this. This also means I have to solve y equals x minus 2 squared for x. It's actually not going to be that bad to do that, but that seems harder. So what I'm going to do instead is let's do vertical rectangles. That seems to be the natural thing to do here. And then our top function is always the line, y equals x. Bottom function is always the parabola, y equals x minus 2 squared. So I'm going to do a vertical rectangle. As I draw that, whoops, that way. Let's do erase, undo our, there we go. So let's go do our, let's draw it as a rectangle here. And then I'm going to rotate around the y-axis, and if you think about the shape that makes, that's going to be a shell. So we're going to use shell method here. So our volume is going to be an integral. We're going to do a dx integral. We have vertical rectangles, so it'll be a dx. X's go from 1 to 4 here, and our shell method is 2 pi times the radius of the shell, which is really the distance from the rectangle to the axis of revolution. In this case, that's x here, and we want that in terms of x. And that gives us sort of the circumference of our shell. And then we just multiply by the height here, which should be the top function minus the bottom function. So x minus 2 squared. Again, let's do square brackets. Just not confused with the parentheses there. So that sets up our definite integral. And now we want to evaluate this. Like the problem finding the area, we know we should get a positive number. So if we don't, it tells us something went wrong. So let's just work on this. I get 1 to 4. I get, what I'm going to end up doing here is probably expanding this x minus 2 squared. So I'm going to get x times x minus x squared would be a minus 4x. It's going to be a plus 4x because we're subtracting. And then a plus 4 will turn into a minus 4 dx. And then what we're going to get is 2 pi integral from 1 to 4. I'm going to distribute the x. I get an x squared minus x cubed. We get a plus 4x squared, so I should probably combine those x squared terms. X times negative 4 is negative 4x dx. And then let's combine those x's, so we only have to do one evaluation with those, or say the x squareds. And if we do one evaluation instead of two, so x squared plus 4x is 5x squared minus x cubed minus 4x. And now we're ready to find our antiderivatives to integrate. So I get 2 pi. 5x squared is going to give me a 5x cubed over 3 minus x to the 4th over 4 minus 4 times x squared over 2. That's 2x squared well, just 2x squared. And I'm going to evaluate from 1 to 4. So now I should write this down. I get 2 pi 5 times 4 cubed over 3 minus 4 to the 4th over 4. 4 over 2 is 2, so minus 2 times 4 squared. And when I subtract, plugging in 1s, that's going to give us a 5/3 minus 1/4, and then minus 2. So there's our value. And again, I would probably write this down, go to my calculator to get an answer. I'm going to work it out by hand just for the sake of, but probably on an exam, I don't really trust my arithmetic, or that, I'll probably make a mistake here. Even now I don't. Let's see, 4 cubed is 64 times 5 is 320. 4 to the 4th over 4, I can make this 4 to the 3rd, cancel one of the 4s. 4 to the 3rd is 64. 4 squared is 16 times 2 is minus 32. And then I get a minus 5/3. Minus a negative gives me a plus a 4th. Minus a negative gives me a plus 2. So what I get is 2 pi times, let's see, 320 minus 5/3 is 315 thirds. Minus 64 minus 32 is minus 96. Plus 2 is going to be a minus 94. And then I have the plus 1/4 hanging out. 315 thirds, let's see, that's actually 105 if you do the division. 105 times 3 gives you 315. Minus 94 plus a 4th. So you end up with 2 pi times, let's see, 11 minus a 4th. So that's going to be 2 pi times 44/4 minus a 4th. So this is going to be 2 pi times 43 over 4. And I can simplify that to be 43 pi over 2. Let's check with the calculator. Did I actually do that correctly through arithmetic? When I do this, I'm going to leave off the pi, just sort of tag that along at the end. So I'm just going to do the 2 times, open my parentheses. What I'm going to get, let's see, I'm going to get, first group is 5 times 4 to the 3rd divided by 3 minus 4 to the 4th divided by 4 minus 2 times 4 squared. And then minus the second group is 5 divided by 3, 5/3, minus 1 divided by 4 is a 4th, minus 2. Close my sort of second parenthesis, close the square bracket, hit enter. I get this, math to a fraction. And again, I made a mistake here, so 45. My guess is, yeah, I can see it's 44 plus 1 would give me 45. Note, I got 11. That plus 1/4 should have been a, or sorry, that minus 1/4 should have been a plus 1/4. That 43 should have been a 45. And I should have gotten 45 pi over 2. So I've made little arithmetic mistakes on both questions. Maybe that sort of accidentally drives home the point that it's good to rely on the calculator to do all the sort of nitty-gritty calculations. Although you may find yourself in a class where you sort of have to share the work, but the calculator can still check if you've got access to one. Next question. We're going to find the volume of the solid formed by revolving the region bounded by y equals x minus 2 squared and y equals x about the x-axis. So note, this is the same region that we had in the previous question. So I'm just going to sketch that up again. I get a parabola like this, and then some line through the origin. This point was 4, 4. This point was 1, 1. And we've got this region we're going to rotate. This time we're rotating about the x-axis. So same setup. I don't want to do horizontal rectangles because it's sort of messy with the functions where the left endpoint changes which function I use. So I'm going to do the vertical rectangles. But now when we rotate about the x-axis, we're going to get a washer instead of a shell. So this is going to be a washer method. And so my volume, I'm going to integrate from x goes from 1 to 4. This will be dx. Washer says do pi times the outer radius squared. So the outer radius is the distance from the axis of revolution, that's the x-axis, up to our top function, which is x. So that's just x squared. I'll put that in parentheses to sort of emphasize it's the function squared. So it's just I have y equals x squared. And then I subtract the inner radius, which is x minus 2 squared, and then I have to square that. So that's really all I get for washer, and it's a matter of evaluating that integral. So what I'm going to get is pi, integral from 1 to 4. So I'm going to get an x squared minus x minus 2 to the 4th dx. So when I look at this, you could expand out x minus 2 to the 4th into a polynomial and integrate. I'm going to do something different here. I'm going to split this into pi times the integral from 1 to 4 x squared dx minus, let's do it this way, minus the integral from 1 to 4 x minus 2 to the 4th dx. And then I'm going to use a substitution where u equals x minus 2 on the second one, so I don't have to expand that out. So what I'm going to get is pi times x cubed over 3, so you'll evaluate from 1 to 4, minus, now here I'm going to have to use a u equals x minus 2, du equals dx, so I'm going to get an integral of just u to the 4th, du, so I replace x minus 2 with u, but I'm going to have to change my bounds. So when x is 1, 1 minus 2 is negative 1 for u. When x is 4, 4 minus 2 is 2, so u is 2. And now I get pi. See, this is going to be 4 to the 3rd over 3. So ugly 4 to the 3rd. Minus 1/3. Whoops, don't close the square bracket yet. It's just the first integral. Minus I have to integrate here still, so u to the 5th over 5. And this is u from negative 1 to u equals 2. So I get pi, 4 to the 3rd is 64 over 3. Really minus 1 over 3. Minus, plug in, I'm going to get 2 to the 5th over 5 minus negative 1 to the 5th over 5. Here. And then when you evaluate that, you get pi times 63 thirds minus 32 fifths plus 1/5. Again, this is probably the point where I would just go plug into my calculator. I might have even not done the 4 to the 3rd over 3 minus 1 to the 3, minus 1 over 3. 4 to the 3rd over 3 minus 1/3. I've skipped that. But what I'm going to get is pi times 63 over 3 is 21 minus, this is going to be 33 fifths. So that's pi times, let's see, 105 fifths minus 33 fifths. So I get pi times 72 fifths, which is 72 pi over 5. Let's see if I actually got the arithmetic right. So I'm going to go to my calculator. I'm going to do the, let's see, 4 to the 3rd divided by 3 minus 1/3, close parenthesis, minus the second bit is 2 to the 5th divided by 5 minus negative 1 to the 5th divided by 5. Close parenthesis, I hit enter, I get this. Math to a fraction. Hey, look, I actually got the right answer. So it should be 72 pi over 5. So in this next problem, we're going to try and set up a definite integral to find the area of the surface obtained by revolving the part of the curve y equals cosine x with x between pi over 3 and pi over 2 around the y-axis. So this is a surface area question. So what we're going to do, let's just draw cosine x. We're going between pi over 3 and pi over 2. So cosine pi over 2 is 0. So our cosine x is going to sort of, well, start here, go down here. That's not a very good drawing. Start here, something like this here. And at pi over 3, we're here, and this is at pi over 2. So our sort of region is this thing here. Oh, sorry. No, not a region. Let's start over here. It's not a region. It's a sort of curve. So we're going to go, we've got a cosine here. So we get to pi over 2. Pi over 3 is back here somewhere. And so what we're going to do is take the curve from here to there, and we're going to revolve around the y-axis. So you're going to take this curve, rotate around the y-axis. So you're going to get something that looks sort of without the curve, something like this kind of shape here. And we're trying to find the surface area of that. Now this side will be curvy here. So when we find the surface area, what we can do is we can either split up this curve along the x-axis or the y-axis. Now, so we can really do the surface area integral as a dy integral or a dx integral. What I'm looking at here is I don't really want to take y equals cosine x and solve for x here. So I'd really like to do things in terms of x here, so I don't have to do x equals some function of y. So I'm going to choose to do this as a dx integral. And I could do an inverse cosine x, but inverse cosine y, but I don't really want to do that. So I'm going to do a dx integral. So my x range is going to go from pi over 3 to pi over 2. And then when I do the surface, I'm going to move this dx out here a little more. Do my surface area, I get 2 pi times the distance from one of my sort of little line segments. So what I'm going to get, maybe in green, is a little line segment here. And then what I'm going to do is think about what happens when I rotate this about the y-axis. Well, it's going to be 2 pi times the radius, that's this distance here. Well, that's just x here. And then the sort of slant height here is going to be square root of 1 plus really f prime of x. This is like our arc length sort of differential here. So the derivative of cosine x, which is negative sine x squared. So we get this integral here as we go. Now, this says set up a definite integral. Later on in this course, we'll figure out how to actually evaluate something like this. This isn't, or no, well, we might. Here, this one's maybe a little complicated, but all we needed to do actually was set this up. So our answer here is literally just this integral here. I personally don't even really care if you take the negative sine x squared and write it as sine squared x, or simplify, like the negative goes away. This is fine. You could plug this into technology and get an answer. Next one. Again, set up a definite integral. We won't have to evaluate. To find the length of the part of the curve y equals e to the tan x with x between 0 and pi over 4. So there's some function e to the tan x. Now, I don't even know what that looks like. I'm going from x to pi over 4. I'm just going to draw some kind of scribble here. So I go 0 to pi over 4. And I'm just trying to find the area along this function here, up to pi over 4. And the integral setup is my arc length. I'm going to integrate. I'm going to choose to do it with respect to x. 0 to pi over 4. It's that square root 1 plus the derivative of sort of y, or dy dx squared. So our derivative of y, let's see, this would be e to the tangent x times the derivative of tangent x by the chain rule. Derivative of tangent x is secant squared x. Here, and then we have to square that, dx. So this is really all we need to do for an answer. Set up some integral that we could then go plug into some kind of software to figure out an approximation. Next question. Let's see, so this is a work question. I'll point out if you're looking at this for the fall 2015 exam, we're not going to do work problems on this exam, so you don't really need to pay attention, but I'm going to throw it anyway for completeness. This says a conical tank has a vertex at the top, a height of 6 feet, and a bottom radius of 5 feet. So let's just draw that. Our tank, it's a cone, vertex, sort of the pointy part is at the top. That's not a very good drawing. Let's probably better there. So it looks something like this, and maybe I should dash this back line here. There. So there's our cone here. It's something like that. It says the tank is full of water, and we know how much work would it take to pump all the water in the tank through a pipe. So we've got some pipe located really at this top point. So this is really the height we're trying to pipe through. So now we're going to want to sort of do some geometry here. So our cross sections, if you look at this, I'm going to draw from the center up here. Let's draw this triangle here. And then each cross section would really be a circle here, or really a cylinder, I suppose, if we did, I guess, horizontal cross sections. And so that triangle, if you look at it, see the height overall is 6. Bottom radius is 5. Now this, you could do Pythagorean theorem. This will be a right angle. So you could do Pythagorean theorem. So 6 squared is 36. 5 squared is 25. You add those together. I guess that's square root 61. I'm suspecting we may not use that, but that's there. And what we're going to do, essentially, is we're going to chop this up into little rectangles and sort of move each, well, rectangle up to the top, but not each rectangle revolved around. So we'll get a cylinder, and we rotate that around, move that to the top. To find the amount of work to do that, the key thing is that each of the cylinder sort of, except for the fact that top and bottom are a very small distance apart, each sort of molecule of water or whatever in that cylinder is going to have to go to the same height to get to the pipe. Here. And so what that allows us to do is sort of our delta work. It's the work to do sort of one of these slices, which I guess would be a cylinder if you rotated that around. It's going to be the weight of that slice. So that's going to be 62, our density, times the volume, which is, let's see, pi times our radius here. Now we want to sort of define an axis here. So I'm going to do my axis. How about we start here at, let's call it y equals 0, and down here y equals 6. So this is y, and we want to figure out this distance here is y. Well, then this distance here, what should be 6 over 5? This should be proportional. So 6 over y equals 5 over, let's call that x here. Actually, let's call it r here for radius. And so in terms of y is going to be 6r equals 5y. So r is 5/6 y. So really this radius is 5/6 y. So we get pi times 5/6 y squared. And then our height will be delta y. So that's just the weight here. So we get 25/36. And like this formula I like to check. If we plug in y equals 6, we'll get 5 for the radius. That checks out. If we plug in y equals 0, we get 0. Okay, so that's the weight of that slab of water. The work is going to be sort of the weight, which is really the force you need to apply to move it, times how far it goes. So the distance it goes is actually y. So we get a times y because the distance to the sort of top, which is where we're pumping it to, is a distance of y. So that's really our delta W here. And that means our work is we're going to integrate from 0 to 6. We get a 62 pi. Whoops. 62 pi. We're going to get a 5/6 y squared. That's going to be 25/36 y squared. We get a y back there, and the delta y turns into a dy. So I just need to evaluate this. So let's see, 62 times 25 over 36 pi times integrate 0 to 6, y squared times y is y cubed. Let's see, 36 and 62, I can cancel a 2. That's 18 and 31. 31 times 25, let's see, that's 775 pi over 18. Let me check that here, actually. 31 times 25, yep, 775. And then when I integrate y cubed, I get y to the 4th over 4. And this goes from 0 to 6. And so what I'm going to get is I'm going to get 775 pi over really 18 times 4 times 6 to the 4th minus 0 to the 4th, which is just 0. And so what I end up with is, let's just use the calculator. It's 775 times 6 to the 4th divided by, on the parentheses, 18 times 4. You get an answer. It's 13,950 pi. And there are units, let's see, feet and pounds here. So this is going to be 13,950 pi foot-pounds. So there's really the work to empty out that conical tank. Next one. So we're going to do a center of mass here. So we want to find the center of mass of a plate with uniform density delta that is bounded by x equals 0, x equals 1, y equals x cubed, and y equals 5 minus x squared. So let's draw this out. We've got x equals 0, x equals 1, y equals x cubed is going to do something like that. Y equals 5 minus x squared is going to do something like that there. Let's find the intersection point. Actually, what I'm concerned about is 0 and 1. Is that x equals 1 to the left or right of this intersection point? So if I plug in 1, x cubed is 1. 5 minus x squared is 5 minus 1 squared, 4. So that's above. So we're really going to chop this at 1. And we're looking at this region here. So I don't need to find the intersection point, which is sort of nice. So that's at 1. That's at 0. That's what we're looking at. So we're looking at this region. We want to find the center of mass here. So we're going to find our moments. Let's do, how about m? Let's do m first. Let's do the overall mass. So our mass is really just the area times our delta, well, with density delta. So we're going to get an integral. And now, do I want to do this dx or dy? Well, dx, if I do horizontal slices, really my right function here starts off with this parabola. Then it's this 1, and then I've got to solve, really, I suppose that's cube root of y here. So that's 3 different integrals, seems like a mess. So I'm going to do everything as a dx integral. So I'm going to get 0 to 1. And what I'm going to get here is I'm just take the top function minus the bottom function. That's 5 minus x squared minus x cubed dx. So that works out to be, let's see, 5 integrates to 5x. X squared is x cubed over 3 minus x to the 4th over 4 from 0 to 1. So that works out to be 5 minus a third minus a fourth, and we can subtract a 0. So let's see, this is 5 minus 4 twelfths minus 3 twelfths equals 5 minus 7 twelfths. 60 twelfths minus 7 twelfths works out to be 53 twelfths. So our sort of, well, the mass with uniform delta, uniform density, sorry, the area would be 53 twelfths. Really, I should have a delta here. But when I do my center of mass, I'm going to divide moment by the mass, and the deltas will cancel out. So I don't really need to worry about them anyway. So that's our mass. Now we're going to do our moment, but in green, let's do our moment about the x-axis. So our x-axis is here, and I'm going to do a, let's see, it's always going to be a vertical rectangle, because those are easier to describe. And what I want to do is think about the moment about the x-axis. So because I'm going about the x-axis, I have to sort of shrink this rectangle into a point at its center. And when we do that, what we're going to get x goes from 0 to 1. I'm going to get really the distance from the sort of center, that point, to the axis of revolution. Now that's going to be the midpoint down to, well, y equals 0. So it's just really the x, or the y coordinate of the midpoint. To find that, I'm going to have to average the top and the bottom function. So I'm going to get top is 5 minus x squared. And I'm going to add the x cubed. And I have to divide by 2 to get the average. Then, that really gives me that distance. I have to find sort of the area here, which is going to give me the mass. I multiply by the top minus the bottom. So that's 5 minus x squared minus x cubed, which is really what we integrated up here for the mass. Do that dx. So this will give me my moment about the x-axis. This is going to be a 1/2 outside, 0 to 1. Note this is a plus b. So let's do it this way. So this is a plus b, where that's my b, here. And then over here we've got really a, and then the same b here, we get minus b. So this is a plus b times a minus b. Now if you know your formulas, this is a squared minus b squared here. So you can use that to maybe help out. That tells me this is 5 minus x squared squared minus x cubed squared dx. So this one, I'm just going to go and expand these. I get a 1/2, integral 0 to 1. Let's see, I get a 25 minus 5 times x squared is 5x squared times 2 is 10x squared plus x to the 4th. I'm going to get a minus x to the 6th. A little bit messy, but I can work through this. So I get a 1/2, whoops, no more 0 to 1. Let's integrate. I get 25x minus 10x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 from 0 to 1. So I'm going to get 1/2. This will give me a 25 minus 10/3, just plugging in x equals 1, plus a 5th minus a 7th. And now I'm getting kind of tired of doing the arithmetic, so I'm just going to use my calculator. So this is 1/2 times, so we have 25 minus 10/3 plus 1/5 minus 1/7. So now that gives me something ugly. I'm going to go to a fraction. 2281 over 210. So it's 2281 over 210. So that's mx. Let's look at my. our moment about the y-axis. You can get a picture here. So about the y-axis, I don't really need to replace this with the midpoint because everything is the same distance from the y-axis. Our y-axis is here. And so what we're going to get is an integral from 0 to 1. We're going to do distance to the axis of revolution. Well, let's just x. So we're sort of indexing that red rectangle with an x. And then times the area, which is 5 minus x squared minus x cubed. So that's our moment about the y-axis, and we just have to evaluate this. So we get a 0 to 1. We can distribute the x. We get 5x minus x cubed minus x to the 4th dx. So that's going to spit out a 5x squared over 2 minus x to the 4th over 4 minus x to the 5th over 5, evaluated from 0 to 1. It's going to end up giving me 5 halves minus a 4th minus a 5th. Again, maybe I'm a little bit lazy here, but I'm just going to go to my calculator. 5 halves minus a 4th minus a 5th. Spits out that, but I'm going to convert it to a fraction. Gives me 41/20ths. Whoops, 41/20ths. Okay, so we have our moment about our y-axis, moment about our x-axis, and then our mass was 53/12ths. And so our center of mass, here, our center of mass, here, what we're going to get is this is really the point x bar, y bar, where the x bar is my, moment about the y-axis, divided by the mass. And the y bar is mx divided by the mass. So in our case, that's, let's see, my is 41/20ths over our mass was 53/12ths. Comma, moment about the x-axis is 2281 over 210 divided by 53/12ths. And I'm going to use my calculator to sort of simplify this. So let's do 41 divided by 20 divided by 53 divided by 12. We get this, and then math to a fraction. Spits out 123 over 265. And then we're going to get, how about 2281 divided by 210 divided by 53 divided by 12. Let's hit enter. We get like 2.5. Go to a fraction, and we get like 45. Was it 62 over 1855? So this is our center of mass. Probably a good idea here. This was a lot of calculation. Let's check if that actually seems like it's plausible with the picture. So 123 over 265, that's about a half. And between 0 and 1, about a half makes sense. 4562 over 1855, that was like 2.45, maybe like 2.5. Let's see. Here we said at this point here we had a 1 is x cubed and a 4. Total height is 5. That's about in the middle of the sort of y range as well. So that seems like a plausible answer. Okay, so last problem here. We're going to find the center of mass of a plate with density delta x. Now, instead of just a constant density, the density is 2x. It's a function of x that is bounded by x equals 0, x equals 1, y equals x cubed, and y equals 5 minus x squared. So if you notice, these are the exact same bounds as the previous problem. So let's just draw this up again. Whoops. So what we've got is like a y equals x cubed, and there's a parabola down, y equals 5 minus x squared, x equals 1 is over here, and we're looking at this area here. And again, we're going to do vertical rectangles because horizontal splits us up into different sort of right half functions here. We're on the y equals x cubed, actually x equals cube root of y, and then we'd run x equals 1, and then we'd have to solve that parabola for x on the rest of it. So it's a little bit of a mess here. But also because our density function is constant if we fix x. So the density is really in terms of x. And what that means is our plate is getting like thicker the larger x is. So on the right, our plate is thicker than on the left. So if you think about what that should do to the center of mass, it should move the center of mass to the right here. So essentially our center of mass was about in the middle before. It shouldn't go somewhere to the right. So let's set things up. Our mass we're going to integrate 0 to 1, and we're going to do our sort of height here. Our height is top function, 5 minus x squared, minus bottom function is x cubed. But now we need to also multiply by the density, which is 2x. Before we could have put a delta in there, but the deltas would have canceled out. Here we really need that 2x. So this will give us not the area of that region, but the mass of a plate using our density being 2x. So when we evaluate this, let's see, we'll distribute, we get 10x minus 2x cubed minus 2x to the 4th dx. So we get 5x squared minus, that'll be x to the 4th over 2, so 2x to the 4th over 4, minus 2x to the 5th over 5 from 0 to 1. So this is going to end up being 5 minus a half minus 2/5. That's 50 tenths minus 5 tenths plus 4 tenths, not plus, minus 4 tenths. Oops. So that looks like 41 tenths. So that's our mass here. Now we're going to have to do our moments as well. So let's do our moment about the x-axis. Same sort of strategy as before. We're going to shrink really our rectangle into sort of a point in its midpoint here, really the middle here. And it'll sort of average out. So what we're going to get is we're going to integrate 0 to 1. We're going to do a distance of that midpoint to the x-axis. That's going to be a 5 minus x squared plus the x cubed over 2, so average of the top and bottom functions. And then we're going to multiply by the sort of mass of the rectangle. So that's going to be the top minus the bottom, 5 minus x squared minus x cubed. But then we also have to multiply by our density, which is 2x. And then we get the dx here. So we set up this integral. The 2's cancel. And then this is the 5 minus x squared plus x cubed times 5 minus x squared minus x cubed. We have the x, so I get 0 to 1, difference of 2 squares. 5 minus x squared squared minus x cubed squared. But then the whole thing is multiplied by this x here, dx. So we get an integral 0 to 1 x times, let's see, it's going to be 25 minus 10x squared plus x to the 4th minus x to the 6th dx. And so what we'll get is an integral from 0 to 1. We have to distribute the x. We get 25x minus 10/3 x cubed. Or sorry, not 10/3 x cubed. I'm trying to integrate already. Minus 10x cubed plus x to the 5th minus x to the 7th dx. And then when I actually integrate this, what I'm going to get is 25x squared over 2 minus 10x to the 4th over 4 plus x to the 6th over 6 minus x to the 8th over 8 from 0 to 1. Then basically I'm going to plug in 1. And when I plug in 0, I get 0, so I subtract. That's nothing. So I'm going to get 25 halves. 10/4 is 5 halves plus a 6th minus an 8th. So what I'm going to get with that, I'm going to get a little lazy again with my calculator. 25 halves minus 5 halves, that's 20 halves, that's 10, plus a 6th minus an 8th. Spits out that. Let's go to a fraction, and we get 241/24. So 241/24. And that's our moment about the x-axis. We also want our moment about the y-axis. So we get an integral from 0 to 1. And then we're going to do a distance to the y-axis for this red rectangle. Well, that distance is just x. And then we're going to get the height of that rectangle, which is top minus bottom. That's 5 minus x squared minus x cubed. And then we need to multiply by the density, which is 2x. So what we'll get here is, okay, a 2, integral 0 to 1. We're going to get x times x is x squared, so you get 5x squared minus x to the 4th minus x to the 5th dx. Then when you go to actually integrate this, we'll get, let's see, 5x cubed over 3 minus x to the 5th over 5 minus x to the 6th over 6. Go from 0 to 1. So that's 2 times 5/3 minus a 5th minus a 6th. So let's just figure this out. 2 times 5/3 minus a 5th minus a 6th. And what I get is, well, 2.6, but that's 13/5. So same thing as before. Really, the only difference between the previous question is every time we find this sort of mass, we have to multiply by the density. The 2x, the 2x. And down here, the 2x. We could have used a delta before, but then when we do the next step, finding x bar and y bar, the deltas would have canceled out, so you don't really need them if the density is constant. Okay, let's do that. So x bar is moment about the y-axis divided by the mass. So that's 13/5 over the mass was 41/10. So that's going to be, let's see, 10 over 41 times 13 over 5. Get a 2, cancel, and I'm going to get 26/41. Whoops. There. And my y bar is going to be the moment about the x-axis over m. So that was 241/24 over 41/10. This one, let's see, so that's 241 times 10 over 24 times 41. Let's just do this as a calculator problem. So 241, I'm going to go back to this point, divided by 24, divided by 41, divided by 10. Go to a fraction, and we get 1205 over 492. Here. So really our center of mass here is, let's see, 26 over 41. And then it's 1205 over 492. Here. So that's really our answer. Now let's compare this to the previous answer. Again, we said center of mass should move to the right. So let's do 26 divided by 41. It's 0.63. And if we go up a problem, we get 123 over 265. Oops, 20. We'll get this. 123 divided by 265. That's 0.46. So it moved over a good chunk here. The y coordinate could change. In fact, it looks like it did. 4562 divided by 1855. So this maybe feels weird that this can change because the density is only in x. But, oh, let's get the decimal first. We get about 2.46. But if you look at our drawing, like sort of different heights are going to have sort of, or different x values are going to have more to the top or bottom here. So sort of weighting different parts. So it should be able to change the y coordinate as well. So we started at about 2.46. We ended up at 1205 divided by 492, 2.44. So it moved not a whole lot, like about a 100th then. Okay, that concludes really our review for exam 1 for our Calc 2 course.